Hello all. In this video, we'll talk about different representations of a graph. Basically, there are two ways to represent a graph. One is adjacency list and the second one is adjacency matrix. First, we'll talk about adjacency matrix. So usually in mathematics, we read about matrix, right? It basically consists of m rows and n columns. A matrix is represented as m rows and n columns, right? So here because if this is a graph which has vertices and edges, but you can't represent this picture in terms of any programming language or in a computer. You have to convert it to some data structure and represent it, right? So for that, first we'll go with matrix representation. So you take how many vertices are there in this graph? 0, 1, 2, 3. Total there are 4 vertices. So what you have to do is you take a matrix of 4 rows and 4 columns. Okay. If you see here, you have 4 rows and 4 columns as well. And each row, you have to add the vertex value. Here, since we took 0, 1, 2, 3, I have added 0, 1, 2, 3 here. You can add, like let's say if you have A, B, C, D here, you can add A, B, C, D as well. Since here the index numbers and the vertices number matches, you don't see any differentiation here. Now what you have to do is, wherever there is a edge, you fill that with 1. So what I meant is, let's say I go to 0. How many edges does 0 has? 0 has a single edge going from 0 to 1. So here in this matrix, go to row number 0 and go to column 1. From 0 to 1 you have a edge, right? So represent that value as 1. Okay. Now from 0 there are no other edges. So what other values you fill it with 0. Now let's go to another vertex 1. From vertex, how many edges you are seeing? 1 to 0 and 1 to 3. So 1 to 0, you add 1 here. 1 to 3, you add 1 here. So whatever are the remaining, you fill it with the 0. And the remaining values in this row should be filled with 0. I have done the same thing here. Now let's go to 2. From 2, how many edges are there? There is only a single edge going from 2 to 3, right? So from 2 to 3, fill it with 1. And all the remaining values, you fill it with 0, right? Now, go to 3. From 3, how many edges are there? 3 to 2 and 3 to 1. So 3 to 2, I filled it with 1. And 3 to 1, I filled it with 1, and the remaining row values I filled it with 0, right? So this is adjacency matrix representation. Now we will see representations for both undirected and as well as directed graphs. Like it doesn't vary, but we can go through both ones. Now we have seen adjacency matrix representation of an undirected graph. Now let's go to adjacency list representation. So what is an adjacency list representation? How you represent it? So if you take this adjacency list representation, it is a list. Okay. Basically, it's an array. You can consider a list. Basically, it's an array. So each array will have linked list. Now what do I mean it? Let's say I have 0, 1, 2, 3 vertices in a graph. Now it will have it will have linked list. You have an array of linked list, and each linked list will have the edges. So what I meant is, now here if you see, you have 4 vertices, right? So 4 vertices. For each vertex you create a linked list, and in that linked list what it will have? It will have the edges. So what we are doing here is, for each and every vertex in a graph, you are creating a linked list, and that linked list contains edges from that vertex. Now if you see here, 0, 1, 2, 3. So this is an array of linked list. So if you represent here list of linked list of node. So this is the adjacency list representation. So you have a list. This is a vertex list, and each vertex you have linked list. So basically linked list is are the edges for this vertex, right? Now what I'll do is for 0, how many edges I have? I have a single edge. So you create a linked list with pointer pointing to 1. Okay. Do you see any other edge? No. Now what should I do? I should point it to null because you don't see any other edges. Now go to 1. How many edges you have? You have 0 and you have 3. Now for 1, I create a linked list with 2 edges, 0 and 3. And it points to null because the tail should be pointed to null. So for one I created a linked list with 0 and 3. Now for 2, there is only a single edge, 3. So for 2, what I did, I created a linked list and I added 3. Now for 3, I see 2 edges. So what I have to do is, I have to create a linked list and add this edge, 3 to 1 edge and 3 to 2 edge. So 3 to 1 edge is nothing but add the node value 1, 2, 1, 2, and then I just point it to null, right? So this is the adjacency list matrix. So basically adjacency list is nothing but our list of linked list or an array of linked list. Basically it will have only the edges. Now let's see the pros and cons of each approach. Now even if a beginner is very like, he can easily understand adjacency matrix representation, but if you see adjacency list representation, it is a little complex. It takes a time for a person to understand it. So that's where the complexity comes for adjacency list. But let's say you see a dense graph is nothing but, let's say from 0, you have dense graph is nothing but a graph with more edges, which is more dense. From 0 I have edges to all vertices. Now from 0 I have just to 1, right? Let's say I add one more edge here, I add one more edge here, and from 1 also let's say I add. From each and every for each vertex there is a path to each and every vertex in that graph. Let's say for one there is already edge to 0 and 3, but there is no edge to 2, right? Direct edge. I add it here. For 3 also I add a direct edge to 0. Like if you have a dense graph which consists of more edges, then it's better to represent it in the matrix, because here now it's not a dense graph, it's a sparse graph. You have more number of zeros compared to 1. Let's say if you have more number of ones, which means more number of edges, then it's easy to represent it here, right? But in the, like, let's say you don't have many edges, it's a sparse graph, you hardly have 1 to 1s here, which means that 1 to 2 edges, then lots of space gets wasted here. Like if you fill it with lots of zeros, then your memory gets wasted. Instead of that, you can just go with the adjacency list, because adjacency list has only edges. Here even if you do, there is no edge, you still have a value for it, right? Here whatever are edges present, you represent them. If there is no edge, you don't represent it here. But here, since from 0 to 2 there is no edge, but still it has a value, be it 0 or 1. So if it is a dense graph, better go with adjacency matrix. If it is a sparse graph, then you can go with the adjacency list. Because if it is a dense graph, if you go with adjacency list, right, there is an additional overhead of pointer. Because in the linked list video, if you see, for a linked list, in addition to the value, you store the memory address of the next pointer as well, right? Here what you do is, let's say if you see here 1 2, what it stores one value, along with it stores address, it stores this pointer also, which means address value of the next node. So additional space will be taken to store the memory address. So if it's a dense graph, just represent it here. You need not store memory address here. but here you need to store the pointers. So that is where the differentiation comes. So like we discussed about pros and cons of each approach, right? Now we have gone through the representation for an undirected graph. Let's see for a directed graph, though it represents same, we can just walk through an example. So this is a directed graph. And how do you represent the adjacency matrix? You first, as I have written here, you take the number of vertices. So 1, 2, 3. You, since you have 3 vertices, take a matrix of 3 by 3. 3 by 3, 0, 1, 2 and 0, 1, 2. From 0, how many edges are there? 0 to 1 and 0 to 2. 0 to 1 and 0 to 2. Fill the remaining row with 0. Now for 1, how many edges are there? Or just a single edge from 1 to 2. Okay, fill from 1 to 2, 1. And the remaining values, you fill it with 0. From 2, is there any edge that is going from 2? No. There are inward edges but not outgoing edges. So fill it with 0. Now let's go to adjacency list representation. Yeah, take an array of link, like take an array. Array size is number of vertices 0, 1, 2, because it is as I have represented here, list is nothing but number of vertices, and in each index you have a linked list, right? So number of vertices 0, 1, 2, and for each index you create a linked list. Now for 0, I create a linked list and I add 1 here. Okay, because it's one vertex. Are there any edges? Yes, there is one more edge from 0 to 2. Add it. Okay. Now point this 1 to the next memory address. Now add it to the null because that is at the tail node. Now from 1, how many edges are there? There is a single edge. So for 1, you create a linked list and add 2. Done. For 2, there is no edge. You create, there is no linked list required for this. Yeah. Yeah, this is the representation, adjacency matrix and adjacency list representation of a graph. In the next video, we'll talk about traversals of the graph. Thank you.